Okay. Thank you all for your patience while I got set up in the new room. Thank you all for your understanding of rescheduling in a different room that's a little bit more cramped. We do have there are some extra chairs up here if people would rather sit on the stairs, and the fire marshal doesn't come in. So, any questions? Yes.
So let T be a tree and vertices.
Okay.
The exact expected number of leaves, number of nodes with 2 children, and then the number of nodes with 1.
Okay. So if I could tree with n vertices, the first question is what's the expected number of leaves? As usual, when I'm faced with an expected value problem, I'm going to try to break it down into the random variable that I'm trying to compute the expectation of into indicator variables. So this is the probability from 1 to n, the sum from 1 to n of the probability that node I is a leaf. And following the analysis that we did with trees elsewhere in the class, this means the node with the ith smallest search key. Okay. And now I remember that when we were analyzing trees before, everything was ultimately phrased in terms of these other indicator variables, I up arrow k, which means node I is a proper ancestor of node k. And I have to ask now whether it's possible to express node I being a leaf in terms of these other indicator variables that we already sort of know how to analyze. Yes?
Why is the node with the I smallest key a leaf?
If it's not always a leaf. If it were always a leaf, that probability would be 1. If it were never a leaf, that probability would be 0. So the number of leaves is the sum over all nodes of 1 if that node is a leaf and 0 if that node is not a leaf. That's all I'm doing is the standard breakdown by linearity of expectation. The expectation of a sum of indicator variables is the same as the sum of the probabilities that each of those variables is equal to 1. So is there a way that we can express node I as a leaf in terms of these other indicator variables that we've already seen? I'm sorry? You're jumping ahead. It's true, but let's try to get there. Let's try to evolve our way to the answer rather than jumping in, because if we just sort of jump in, then it's hard to extrapolate to any other problem.
Node I is a leaf if it is not a proper ancestor of any other node.
Right. So node I is a leaf if and only if, sorry, that's not an if and only if and only if this this indicator variable k is an ancestor of I is always 0. So I'm glad I was doing this in pencil.
I is the proper ancestor of k.
Oh, you're right. So undo. I had it right before. Good. So a leaf is not a proper ancestor of anything else. Not a leaf does not have any proper ancestors. What would that be? The root, right? And so what's the expected number of roots? 1, right? Good. Okay, so all right, whatever. So I want to know what is the probability that the node, under what conditions is the node a leaf? Well, it's not a proper ancestor of anybody else. And at this point, I might be able to do some sort of union-y bound thing, but I think it's actually maybe better to sort of step back and remember, okay, there was this other characterization of what is the probability that I is an ancestor of K, and that's, I is an ancestor of K if and only if node I has the smallest priority among all the nodes between I and K. Okay. So if the statement I is never a proper ancestor means that if I write down the priorities, and I'm sorting this left to right by the search keys. So the box I'm drawing here on the left, this is the priority of node 1. The box I'm drawing over here on the right, this is the priority of node n. And so I look at the priority of node I. What this is saying, this statement is saying that if I look at any box that starts or ends with node I, this is not the smallest in that box. Okay? So maybe there's another way of expressing that condition that doesn't involve thinking about quite so many boxes. Yes?
Can you explain the box thing that you just said again?
Okay, so the key to the Treep analysis was that because the priorities are generated uniformly at random from a real interval, they're all going to be distinct. And because of the structure of the Treep, the only way that I can be an ancestor of K is if in this range of nodes, the smallest priority is I. If the smallest priority is in the middle, that node J in the middle is going to be the least common ancestor of I and K. If the smallest priority is K, then K is going to be an ancestor of I, and everything in between I and K. Okay. So being a leaf means that for every box that I draw like this, this number is not the smallest thing in this box. And in particular, that's true for this box, where K is just equal to I plus 1. And it's also true for this box, where K is equal to I minus 1. And I claim that just thinking about those two boxes is enough, right? If the priority of node I is bigger than the priority of node I plus 1, then the node I can't have the smallest priority of any box going to the right because node I plus 1 is smaller. Similarly, an argument on the left. If this priority is bigger than that one immediately to the left, then this priority can't be the smallest in some box that goes off to the left because I minus 1 is going to be smaller. And so ultimately what this means now is that I is a leaf if and only if priority of I is bigger than both priority of I minus 1 and priority of I plus 1. Or in other words, priority of I is a local max, which is what was suggested over here. Okay. So this is the conceptual leap. And so I need to stop now and ask for questions before I go on to the mechanics of actually computing the answer.
I just want to be clear. The two statements where I is a proper ancestor of node K and node I is smallest priority and I to K, they're like the same identical thing, correct?
Right, so the thing in blue is the definition,
Definition.
and the thing in black underneath it with the if and only if arrow, that's a lemma that we proved in class. But it's really sort of the key observation that makes the analysis of treeps work, that makes the analysis for randomized quicksort work. So it's important to remember it, and by remember it, I mean write it on your cheat sheet.
So if it's not a local maximum, it guarantees that it's not a leap.
Yes, if it's not a local maximum, that guarantees that it's not a leaf. So, for example, if the priorities looked like this, in those last three nodes, 2, 3, and 5, well, now I look at this box 3, 5. 3 is the smallest priority in that box, and therefore I know that this node on the left is an ancestor of this node on the right, and therefore I know that this node on the left is not a leaf, because it's the proper ancestor of something.
But what if the 2 and 3 is actually put into the same branch, and 5 is actually on the other branch?
Then I wouldn't be looking at this example. I'd be looking at a different example. But, I mean, the argument is if the node in the middle has a smaller priority than the node immediately to its right, then the node in the middle is a proper ancestor of the node immediately to its right, and therefore it's not a leaf. G/right/left/. Okay, so this means that if I go back up to the main argument, this is the same as sorry, screensaver. This is the same as asking what is the probability that node I is a local maximum. And now we get to the mechanical part. Okay, so I look at a particular, I imagine this array of priorities, and I look at a particular one and I ask, what's the probability that this priority is bigger than either of its neighbors? And there are two answers that come to everybody's mind, and one of them is correct and one of them is not. So can somebody give me the incorrect answer first? What is the probability that this priority is a local maximum, meaning it is bigger than the priority to its left and it is bigger than the priority to its right? Yeah. Okay. That's not the right answer, and it's not the most common wrong answer. 1/4. That's the most common wrong answer. And the argument for why you would guess it to be 1/4 is, well, these priorities are random, so if I look at any particular pair, either one is equally likely to be smaller. So node I has a 50-50 chance of being smaller than node I minus 1, and node I has a 50-50 chance of being smaller than node I plus 1. 1/2 times 1/2 is 1/4. And the mistake in that analysis is that those two probabilities, those two events, are not independent. You can't multiply probabilities unless the events that you're dealing with are independent. In fact, there are 6 different ways, 6 different permutations that these 3 priorities could be in. It could be small, middle, big, small, big, middle, middle, big, small, big, small, middle, small. Okay? And in exactly 2 of those, the one in the middle is a local maximum. Which means the probability that this node is a local maximum, it's out of these 3 priorities, what's the probability that this one is the largest? 1/3. Okay? So what I would like at this point to write is sum from I equals 1 to n of 1/3. But there's a little bell going off in the back of my head that says this is not exactly right. The boundary cases. So what's the probability that node n is a local maximum and therefore a leaf? 1/2. Same with node 1. So what in fact I need to write here is not the sum from 1 to n, but the sum from 2 to n minus 1 plus 1/2 plus 1/2. And this comes out to n minus 2 over 3 plus 1, which is n plus 1 over 3. Okay, so this is the final answer. Roughly n over 3, but a little bit bigger because the smallest and largest nodes are slightly more likely to be leaf. Yes?
Where did the 2 1 come from again?
Node 1 has 50% chance of being a leaf. Node n has a 50% chance of being a leaf. Yes?
So even the leftmost is the smallest tree,
Yeah?
then why isn't it older?
Because it might be the root. It might have a right child. Yeah. Yeah.
Can you also argue by saying that if you, like from node 1 to n, any node I, any node's I parent would be either on the left, immediately on the left or immediately on the right? Like, and because it's a binary search tree, and but for node I to be a leaf means that it cannot be a parent, so it has to have the highest priority among just its adjacent nodes.
Yes.
And that would
Yeah, I mean, this is the right intuition. The important thing to remember is on an exam, what you would write down is n plus 1 over 3. Right? Proofs are not required unless we explicitly say prove in bold italics. The word prove does appear in bold italics on the midterm, but you'll notice it didn't appear on this exam. So the intuition, oh, right, it's about a third, and you write n over 3. At this point, you've gotten 2.5 out of the 3 points or something.
So for the 1 child or 2 child cases,
Uh-huh.
would you only change the boundary conditions since there's still?
Yes, that's exactly right. For the condition, when does node I have 2 children? That's when its priority is a local minimum. When does node I have 1 child? When it's not a leaf and when it's not a node that has 2 children. Or in other words, when it's neither a local maximum nor a local minimum. And so for the nodes in the middle, that's a third, a third, a third. The only thing that changes are the nodes on the ends. So in particular, the probability of being a local minimum is exactly the same as the probability of being a local maximum. Okay? So the answer for how many nodes have 2 children is, again, n plus 1 over 3. And then the probability of having 2 children, if you're node 1, is 0, because you can only have a right child. And for node n, it's 0, because you can only have a left child. And in that case, the answer is n minus 2 over 3. And as a sanity check, if you sum up these 3 answers, they sum up to n, which is good because you took the expected number of nodes with 0 children, the expected number of nodes with 1 children, the expected number of nodes with 2 children. By linearity of expectation, that had better give you the expected number of nodes, which is n. And in fact, you really only need to go through this argument, the formal, the local argument, for 2 of the 3 cases, because you know that the answer for the third one is n minus the sum of the other 2. Okay. More questions about leaves and trees?
Do you have to count for, do you have to count for n equals 1, the special case?
Very good question. Really, yes. On an exam, no. Yeah, good question though. Although for the case, also n equals 2 is a little bit problematic. Is how many nodes in a tree with 2 nodes have 2 children? None. So.
Can we move on to a different one?
Yeah.
I have one here. It's a dynamic programming language.
Okay, good.
It's paragraphs of answer.
Okay, we've got one vote for dynamic programming problem.
What's up, bro?
Oh, is it
There's
dynamic or is it
nuts and
randomized?
bolts.
Wait.
Yeah.
It was randomized actually. Sorry.
Number 5.
The top one.
The top one.
2.
Political convention, that's a divide and conquer algorithm. Okay. So this is really, this particular question is actually more in scope for the old 473 when we talk about divide and conquer algorithms, or for 374. The question is, you're at a political convention, and if you're a member of the same political party, when you meet somebody, you're actually willing to shake hands. If you're not, you growl and you show your Glock. And the question is, by introducing people to each other, how quickly can you find one member of the majority political party? And the answer, there's a number of ways to do this, is you can actually do it by only introducing order n pairs of people. So one way to do it is you line people up in pairs. If people shake hands, you send one of them out of the room. If people growl at each other, you send them both out of the room. And then you can observe that the majority party hasn't changed. As long as one party has strictly more than half of the members, that's true even after you've done this filtering. You recursively filter until you're down to one person, but that gives you a descending geometric series, so it all adds up to order n. There are a couple of other ways to do it, but since we didn't really talk about divide and conquer stuff
We were just
so
opening
much.
it when we were looking at it.
Yeah.
Thank you.
Okay.
Yeah, there was a problem in the notes for nuts and bolts. Problem 9.
I'm the largest.
Oh, that one. Finding the largest bolt.
Yeah, and then
Not necessarily a good exam problem, but because it's much more mechanical. So the idea was, you pick up a bolt, you pick up a nut. If the nut is smaller, you drop it. You pick up another one. If the bolt is smaller, you drop it. Pick up another one. It comes out to about 3n/2. Because you either run through all of the nuts and about half of the bolts, or you run through all of the bolts and about half of the nuts, depending on some case analysis. But this is better as a homework problem to kind of get used to playing with the material than as an exam problem.
Nuts and bolts, number 5, please.
Surprisingly, I don't have these all in my head. So.
This one's algorithm 1, so.
What's the? Give me 3 words, and I should be able to. This is the random walk stuff. Let me just say there won't be random walks. So, yeah. And part of the reason I'm saying that is, first of all, that was a CS 573 exam question, which meant most of the people taking it were PhD students. And secondly, they didn't do very well. Good, left spine. All right, and after this, I'm going to call a moratorium on treat questions. Okay, because we got to do some other stuff. Okay, so the question is, what's the expected length of the left spine? Okay, so the left spine is what you get when you follow left pointers, but there may be right pointers as well. Okay, so this is the left spine. Again, because this is a question about treeps, I'd really like to be able to phrase this in terms of these indicator variables. Something is an ancestor of something else. So is there a way to write, this is the sum over I of the probability that I is on the left spine, again. But is there a way of expressing this node is on the left spine in terms of an ancestor relationship?
I is the ancestor and I is greater than P.
What's K?
You write it, I and P later. I is the ancestor of K and I is greater than P.
What's K?
K is
Now I'm asking for you to give me an expression that means I is on the left spine. There is no K. There's only I.
Oh, alright. So I is not a. So K is an ancestor of I.
What is K? K is a free variable. I haven't defined it, so it can't possibly be. Unless you like put a sum over all K or for all K or there exists K. K is an unbound variable. It doesn't mean anything in this context. Unless you give it a context. Yeah?
Priority is larger than any other element.
So I's priority is larger than any other element to the left. Okay? So I want to say that the priority of I is larger than the priority of anything from 1 to I minus 1. Right? Is that what you want? Larger? Smaller? Smaller. Okay, so let me write this a different way. Node I is on the spine if and only if it is an ancestor of node 1. Except this is not quite right because the arrow means proper ancestor, so I have to remember to add 1 at the end. But now remember, what's the probability that I is an ancestor of node 1? And again, I remember this because it's on my cheat sheet. This is the same as among all nodes from 1 to I, node I has the smallest priority. Well, every node between 1 and I is equally likely to have the smallest priority, so this probability is 1 over I. And in fact, that's true even when I is equal to 1. So I don't have to special case that. So this is the sum from I equals 1 to n of 1 over I, which is by definition the nth harmonic number. That's the answer. And yeah, this is less than natural log of n plus 1. It's big O of log n. But the answer is the nth harmonic number. Yeah.
What's node 1 in this case?
1. Node 1, the node with the smallest key. The node furthest to the left. The one that gets at the end of the left spine where I get to by chasing left pointers. Okay? Good.
Can you do a deep question
Yes.
for using a tree? So there's like the minimum number of rounds in the top pair.
Ah, good. Okay. So I'm trying to remember in the statement of the problem, was the tree binary or not, or just general? Let's assume that it was binary because that'll make it easier. The generalizing to non-binary trees is not so hard, but let's not just do it yet. Okay, so the problem is the following. I have a binary tree, and one of the nodes in the binary tree knows a secret. So imagine that this is, can't actually see the secret. Okay, let's try that again. One of them has a secret. In a single day, I can pass the secret to one of my two children. And then that child will, on the following day, pass the secret to one of its children, and meanwhile, I will get to pass the secret to my other child. And so the question is, how many days do we need to distribute this secret to everybody in the tree? Right? So each day a marked node, every marked node marks one unmarked child. And the question is, how many days do we need to do this so that before everybody's marked? And I want this number to be as small as possible. The freedom of choice that I have is whether the first time I have an opportunity to mark one of my children, do I mark the left child or do I mark the right child? Okay, and so this smells like a recursive backtracking dynamic programming algorithm, because when I say I've got two options and I don't know which one to try, the appropriate answer is that I try them both. Okay, so let me write minimum days of V. This is the minimum number of days to, let's call it flood the subtree rooted at V, where I assume at the beginning of day one, V is marked and none of the proper descendants of V is marked. Okay, and now I can write this as a recurrence. If V is a leaf, we don't need to do anything. Okay. The only node in the subtree already knows the secret. It's already marked. I don't need to do any additional work. At the end of day 0, the entire tree is marked. Okay. Then the question is what to do if V is not a leaf. Now there's actually a couple of cases here because we don't know whether V has one child or two, but let me write down what happens if V has one child, which I'll call W. In this case, the answer is going to be 1 plus minimum days of W. On day 1, V marks W. On day 2, W wakes up and does whatever it does recursively. So the other possibility is if V has two kids, which I'll call L and R. Now in this case, after the first day, one of the nodes is going to be marked, and then after the second day, the other node is going to be marked. And so I've got a minimum of 2 choices. But let's say that I mark L first, and I mark R second. If I mark L first, then L is the subtree rooted at L is going to be flooded after this many days. And then node R's subtree is going to be flooded after this many days. But I have to combine these two things somehow. And I want to take the maximum of them because I'm not doing the left and then when it's all done starting on the right. I don't want to add. I'm going to do the left and then there's a 1 second delay and then I'm going to do the right and they're going to progress in parallel. So what I want to write here, actually let me move this down and say this is either, it's the max of these two. And then similarly, sorry, let me move this down a little bit more. And the other possibility is RL. Okay, So I have a choice. I either mark L first, and then the subtree rooted at L will be flooded at the end of 1 plus min days of L, or and the right subtree will be flooded at the end of 2 plus min days of R, or I'll go the other way. And whichever one of these two maxima is smaller, that's the one I'll take. Okay. Now there are a couple of other ways to phrase this. So for example, I can decide which of those two minima I want based on whether min days of L is greater than or equal to min days of R. And so I could phrase the case analysis differently by saying, if it takes the subtree on the left fewer days to flood, then I should do it first. But I'm just going to be crude and say, okay, fine. I just drew out the cases. I don't know which one to do, so I'll try them both. I don't know which one to do, I'll try them both. Okay, so I have a function, I have a recurrence. The thing that I want to compute, of course, is min days of the root. This is what we want. What sort of data structure could I memoize this recurrence into? The tree. And then what sort of order would I evaluate the recurrence to fill the post order? Okay, so memoize in T, eval in post order, or eval using depth first search, and then what's the running time? It's, well, depending on whether it's said a tree with n nodes or a tree, it's order n time. At every node, I need to evaluate this expression, which looks complicated, but it's order 1 lines of code, and so it only takes order 1 time. Yeah.
Wouldn't they only just want to pass down a message to the child with more children?
No, because there's a slightly subtle relationship here. If the tree is, say one subtree is just a long path, and the propagation is going to go very fast. If the other subtree is big and bushy, it may have fewer nodes, but actually take longer to propagate because there are delays built in no matter how you go down. Okay. So on an exam, hey, here's this clever idea. No. Don't do it. Right? You need to be thorough and stupid. Okay? If you say, oh, there's this quick optimization that can be very clever. Why are you being clever? It's already linear time. And even if you can improve the time on an exam, write down the less clever solution first, so that we can give you some credit for it, even if you then supersede it by something that may or may not work.
Can you just quickly talk about how you would induct on 2 variables or more, like in the binomial tree, where you have both k nodes and
Right.
t depth?
So before I go on to that question, it's a good question. Are there any other questions about this particular dynamic programming problem? Yeah.
Question on the grading. So
Uh-huh.
after we read out our like English description and our recurrence, for the rest of the points, is it fine to say memoize in T, evaluate in post order, ON time?
Yes.
All the points.
Yeah. That's 1 point, 2 points, 1 point.
We don't have to explain.
No.
Okay.
No. The hard part of dynamic programming is getting the recurrence right. So most of the points are going to getting the recurrence right. Yeah.
So what is the approach for an n-ary tree? Like the same.
For an n-ary tree,
Go down like the maxes.
this is why this is the difference between a homework problem and an exam problem. For an n-ary tree, you've got a choice of which node to look at first, and then recurse on everything else. And at this point, it really does pay to argue that I want to consider the children in order of decreasing value of min days. So recursively evaluate min days of my children, and then I need to sum them up, but with the first child having a penalty of 1, the second child a penalty of 2, and so on. And that takes a separate proof to argue that considering the children in that order is actually the right thing to do, which is what makes it not a good exam problem. Right? That's a case where we're doing the optimization on top of the sort of stupid, let's just try all n factorial possibilities. Because by doing that optimization, we take an exponential time algorithm down to something polynomial. Yeah.
Is there anything wrong with just doing 2 plus the max of min days of my left, min days of my right?
Yeah, it's possible that that's off by 1. If you just say 2 plus the max of those 2, then technically you're penalizing the sooner subtree an extra day. And if the 2 subtrees in fact would finish at exactly the same time, then you've added 1. Yeah.
What if I just stored min days of L and R into temporary variables and didn't memorize anything?
That would also be fine.
Okay.
Right. So every node actually stores min days of its left child and min days of its right child. Then it does the constant time thing and propagates its min days up to the parent. It's the same thing. It's the same thing. So if you wrote this down as, and then I evaluate this recurrence with using a post-order traversal of the tree, you're 9/10 of the way there. The only thing you have to say something about is, why don't I want to call min days twice, min days of R twice? Oh, because I write it down. Okay, now you're done. Any other, yeah, sorry.
So like, are we optimizing on the fact that like every single day, if it's able to, a node will send a message out because?
Yes.
Okay.
Yeah. So I'm sweeping under the rug one detail, which is that it is in fact the right thing to do is when I have the opportunity to send out a message, I do. When I can mark a child, I do, because delaying can't make me faster. Right.
So that's like something we can just like say.
Yeah, in this case, I think it's obvious enough that you don't need a separate proof of that. Okay. All right. Yeah, one more question. Sorry. Yes.
I was just going to say you were previously going to go over the 2 induction.
Yes, the 2 variable induction thing. I'm trying to figure out a good problem to do this on, because it's difficult to imagine doing this in the abstract. It's much easier if I have an actual problem in front of me. I'm sorry?
Use an exam problem.
Like I said, I'm struggling to come up with an example. Okay, somebody said something about chocolate. What's the chocolate bar problem?
Break it in half or whatever, right? Down a line. I forgot the exact details. You break along a line.
Okay,
and
so
that picks n-1 breaks or something.
right. Okay, so the one version of the chocolate bar problem is I have an H by W rectangle of chocolate, and in a single turn, we're gonna alternate turns, say, and in a single turn, I get to draw a line down one of the grid lines and break it into 2 pieces, and then it's your turn. You can break it in one of the pieces into 2 smaller pieces, and it's my turn. I can break one of the pieces into 2 smaller pieces. Your turn, my turn, your turn, my turn. And eventually, I will have broken the chocolate into little 1x1 squares. And the question is, how do you play this game well? You want to be the person who doesn't have any pieces of chocolate left to break gets to eat all the chocolate. Okay. Which means either you win if you like chocolate, or you lose if you don't like chocolate that other people have had in their hands. But in either case, decide what the winning condition is. Either the last person to break wins, the last person to break loses. How do you figure out who wins? And you can turn this into a dynamic programming algorithm where you say, well, I don't know which way to break the h by w rectangle. I've got w choices, or w minus 1 choices to break horizontally. I've got h minus 1 choices to break vertically. But then somebody smart comes along and says the number of moves is exactly hw minus 1. And then you can say, oh yes, there's an induction argument here where I induct on the size of the rectangle, and I've got two variables, h and w. Or you can multiply them together and say, I'm going to do induction on the area because the two smaller pieces each have smaller area. And now I only got one variable. And notice I've immediately jumped to strong induction. Or you can reason that every time you break the chocolate bar, you increase the number of pieces by 1. You start off with one piece and you end with HW pieces. And you're done. So the number of moves is the area minus 1 because you go from one piece to area pieces in steps of 1. So it's a good problem it's a really, really bad problem to give in a class where I'm constantly saying, don't be clever. And so, the answer to derive an algorithm to show who wins is, input h comma w. If hw is even, I win. If hw is odd, you win. Constant time. So in general, the kind of thing that we were asking for, say, I want to do an inductive proof where I use this identity for binomial coefficients. So I want to prove that something. I want to count something as a function of n and k, and the right answer, I claim, are the binomial coefficients. If I look at this formula, I notice, at a very high level, think about this as though you were thinking about dynamic programming. Okay, so there is a dynamic programming algorithm to compute binomial coefficients straight from this recurrence, which is, well, I go, n in one direction and k in the other, and then before I want to compute any particular value of n and k, I need to compute these two things immediately above it, one directly above and one above and to the left. And so if I had this pattern of recursion, what order would I want to fill the array? So, it's a two-dimensional array, so I'm probably going to have two nested for loops, one over the rows and one over the columns, but I have to decide whether to do the rows left to right or right to left, the columns top down or bottom up, and I have to decide which is the inner loop and which is the outer loop. So in this particular case, what should I do?
Row major.
So I should do row major. I do the rows from left to right, and I do the columns, I do each row from left to right, and then in the outer loop, I consider the rows in order from top down. Is this the only order that matters? Is this the only order that works? No. What else could I do? I could do column, but I want to poke it a different direction here. Do I have to do the rows from left to right? No. It doesn't matter what order I do the rows. These rows, in fact, I could consider the elements in each row in whatever order I want. There's no natural ordering on the rows within a row. Okay? There's no natural ordering on the second argument, k. Now, go back to induction. I need to consider smaller values of n before I consider the value of n I'm interested in. So I'm going to do induction on n. But the pattern of recursion doesn't require me to have any ordering on k at all. So I'm just going to say for all k. I'm not going to do induction. Induction is really meant as a way of considering things in the correct order, but there is no correct order. Right? Now, I do still have to worry about boundary cases, and that means I may have to consider the case k equals 0 separately and k equals n separately. But in between, I'm not doing induction on k. I'm arguing out about a particular pair nk in terms of smaller n, whatever k is. And so I will still consider all possible pairs nk. So in fact, I'm only doing induction on one of those two parameters. And that was really the pattern of induction that we had in the official solutions for that problem on homework 0. Now, as you noticed, you could also have said, let me do column major order. So in the inner loop, I need to go down, and in the outer loop, I need to go left to right. And in that case, because you've chosen the priority order of those variables, you're forced into doing a nested induction argument. In the inner proof, you're doing an induction by n, and in the outer proof, you're doing an induction by k. And if it sounds like I'm using the word proof in the same sense that I would use the word loop, you're paying attention. That's what you're doing. Right? The pattern of going through the table in the nested loop order is exactly the way you would structure the proof. So in that case, you have two variable induction, but you would separate it out into an outer induction proof and an inner induction proof, each one being careful to do them in the right order. The way you figure out which one of these options is the right one is you do exactly what you do for dynamic programming. You draw the picture, you figure out what pattern of arrows works. That gives you a sense of what to do. And with enough practice, you glance at the recurrence and say, everything on the right is smaller n. That's enough. I should just do induction on n. Okay. Yeah. Yeah.
Can you go over tail inequality?
Sure. Good. So again, struggling to come up with an example. But here's an example. Suppose, for example, I wanted to prove that the probability that let me say this differently. Suppose I wanted to prove that the number of nodes on the left spine is big O of log n with high probability. So this means with probability 1 minus 1 over n to the c for some constant c. Okay. Now, I've expressed being on the spine as the sum of a bunch of indicator variables, right? And so I would like to be able to say, oh wait, I know something about how to bound the probability that a sum of a bunch of indicator variables is much bigger than its mean. Because I look on the back page of the exam, or on my cheat sheet, and I notice this bizarre expression that says 1 plus delta times the expected value mu is at most e to the delta times 1 plus delta to the 1 plus delta all to the mu, where mu is the expected value of this variable x. And delta is just some parameter that I want to throw in. Notice I said this is on the back page of the exam. Okay? Okay. Now, for the sake of argument, let me make the assumption that those indicator variables up there are mutually independent, because that's a condition that you need in order to apply this inequality. Okay? But let me just start with that. Well, I know what the expected value of x is. It's h of n. That's what we figured out already. right? Which is, morally, this is about log n. And so let me just figure out what should we use for delta? 10. Okay, let's figure out what's the probability that x is bigger than 10 times the natural log of n. Well, that means that in this case, delta is equal to 9. This is at most e to the 9th over 10 to the 10th to the natural log of n. This is some number that is clearly very, very small. I don't know what it is, but it's very, very small. And so I can do the game that I usually play with logs. This is the natural log of e to the 9th over 10 to the 10. This is n to the minus some constant. And now I'm done. I don't have to figure out what the constant is. 10 to the 10th is clearly bigger than e to the 9th. And so that fraction is less than 1, so the log of that fraction is negative. I get n to the negative constant. That's all I wanted. There was a question, how did I do that switch? A to the log base b of c is equal to c to the log base b of a. This is one of these things that should just be on your cheat sheet. This is one of these things that, especially when you're playing with things that you might have logs up in the exponent, it's just useful to be able to swap the base with what the argument of log in the exponent. Now there's a separate question, which is, how would you prove that those variables up there are mutually independent? That's a bit more complicated. Yeah?
So 2 questions. Would
Yep.
you just be given that they are mutually independent on the exam?
In this particular case, yes, you would be given that they're mutually independent.
And then the second thing is that, so the work for this problem would be finding the expected value of x and then just plugging it into the formula?
Also realizing that this is the formula that you need to apply, because there's like 5 different versions of Chernoff's bounds, and there's Chebyshev's inequality, which wouldn't give you Chebyshev's inequality would give you a probability that looks like 1 over log n, which is not enough to be high probability. So just recognizing which inequality you need to apply, how to plug in the parameters the right way. The actual value of the number you get at the end is not what we care about.
Yeah. Great.
Yeah.
Are they labeled? Like which one's Chebyshev and...
Yes.
Okay.
Yes. You'll see. I believe in 3.5 hours. Yeah.
I'm just going to assume this is a DP question. So on the final of spring 2015, there is a question on dominoes and whether you can tile a board with a couple of missing.
No, that's not a dynamic programming question. That's a flows question. We'll see that later in the semester.
Okay.
That's in scope for midterm 2. So in a month from now, please bring that question back.
Okay.
Yeah.
There's another question where you have a plane with dots and they're going like a staircase.
Okay, so here's my plane with dots. And I'm going to say that a point is Pareto optimal if there are no other points above and to the right. Okay. The question is, what's the expected number of Pareto optimal points, given that I've got n points in this unit square that are random. Okay, so there's this sort of notional staircase that, this one's also, okay, that I can draw. And so the question is, on average, how many points are on the staircase? And as this question was asked on Piazza, and I pointed out that it is possible using, the fact that these are uniform numbers over the square to express the probability that any particular point is Pareto optimal as a double integral over the appropriate probability density function. Don't do that. Okay. The right way to think about this is to let x1 through xn be the points in left to right order, and then ask, what is the probability that point xi is Pareto optimal? Because this expected value, again, I can express as the sum of a bunch of probabilities of indicator variables. But the question, the trick here is to realize that I can order the points in that sum however I like. Once they've been generated, I don't have to think about them, and this was the point that I threw first, this was the point that I threw second. But after the fact, I'm going to sort them from left to right. Okay. And so in particular, let's look at, what's the probability that point n is Pareto optimal? Yeah.
That no points to the left of it are greater.
No points to the right are higher.
Right.
Yes. So when I was a kid, before I learned to drive, I had a very, very hard time distinguishing my left from my right. And so I used to explain to people that sometimes I could swear this is my right hand. And more than once, I told that story by saying, and sometimes I would explain this by saying, sometimes I could swear this is my right hand. People go, what? And then somebody would say, well, yeah, because it is your right hand. No, it isn't. And I've actually told that story like this. So, this side, to the right, nothing is higher. So, if I take the rightmost point, what is the probability that none of the points further to the right are higher? 1. Right? So, this is 1. Great. Now, let's look at the leftmost point. What's the probability that the leftmost point is Pareto optimal? 1 over n. Because when is the leftmost point Pareto optimal? When it's the highest point. But the y-coordinates of these points are random. The fact that I've ordered them doesn't change that fact. I've ordered them by the x-coordinates. The y-coordinates are still generated uniformly at random. This should remind you of keys and priorities, right? So in general, what's the probability that node I, right? So this is the ith point from the left. What is the probability that node I is Pareto optimal? This is 1 over. Well, it's out of all of these points, point I has the largest y-coordinate. How many points is that? That's n minus I plus 1. And now, if I sum up this over all I, any guesses? Yes. I will point out to you that this is exactly the same problem as the left spine. Exactly the same problem. And so in particular, that means if somebody said, prove that with high probability the number of points on the staircase is big O of log n, that's how you would do it. Yeah?
Would it be possible for you to explain briefly the ties between that and priorities? And,
Okay, so what's weird here is what I really want to imagine is that the x coordinates are the keys and the y coordinates are the priorities. What's different from the normal analysis of treeps is that with treeps, I normally assume that the keys are generated adversarially. They're generated by some user. They're not random. I don't know what they are. But the very first thing that we do with the keys is we abstract them away into just the ranks of the keys. We don't care what the precise key values are. We only care about the smallest, second smallest, third smallest. It's exactly what we're doing here. We don't care about the precise x coordinates. We only care about the smallest, second smallest, third smallest. And at that point, we're making exactly the same arguments that we made for trees. Yeah.
I know you said it was easy, but can you just quickly, 2 lines, do a with hyperobability argument for this one?
Sure. So, Turnoff says the probability that this is bigger than, say, 10 log n. This is supposed to be 1 plus delta times the expected value. So delta here is 9 because mu is hn, which is about log n. This is at most e to the delta over delta plus 1 to the delta plus 1 to the mu, these power. And this is n to the minus constant. 10 is 1 plus delta. This is, delta is 9. Sorry. I picked a constant. So the question is, why did I pick this particular value? I wanted something big enough that it would work out. So I picked a large enough number that I thought it was likely to work out, and it did. In fact, I could probably plug in 3 there and it would still work. But then it would be a little bit less obvious how to do the calculations, given that you're not allowed to have a calculator.
Is there a useful summation cheat sheet that I can add to my cheat sheet somewhere?
Summations, what sort of?
Just like whenever we come across a summation of probabilities, like
geometric series.
Yeah,
So,
series.
okay. So I will show you the 2 summations that come up over and over again. Okay. These really should be on your cheat sheet. One is that one, which you've seen a bunch of times. The other one is geometric series. But the only thing you really need to know about geometric series is up to big O, only the largest term matters. This is how, for example, you get. So in 374, you might have seen examples of this with like linear time selection. If you did that, you spend linear time scanning the whole array, and then you recursively consider half of the array, and then you recursively consider half of the array again, and so on. That's n plus n over 2 plus n over 4, and so on. I can plug that in here where alpha is equal to 1/2, and I would get the constant 2. But the important thing there is, because it's a descending geometric series, only the largest term matters, just put a big O around it. This is also how a lot of the recursion tree stuff works. In a lot of divide and conquer recurrences, you either just have the same work at every level, and so you count the number of levels, or most of the work is at the root, and you just put a big O around it because it's a descending geometric series, or most of the work happens at the leaves, and you just put a big O around it because it's an ascending geometric series. But this is really what it boils down to. And otherwise, there's this one, which is if you sum up a bunch of polynomials, you increase the degree of the polynomial by 1. You might also recognize this formula if I had replaced this sum with an integral. Sums are really just integrals. The same is true here. The integral of 1 over x dx is natural log of x. It's the same thing. This geometric series thing, this is a definite integral from 0 to infinity. It'll work out to some constant. It won't be this constant, or it will be, what is it, natural log of alpha. But this is the first two terms in the Taylor series for natural log of alpha. So if you remember calculus, summations are easy. If you don't remember calculus, learn the summations and then calculus is easy. Ish. Yeah.
In the problem on Pareto optimality,
Yeah.
are the xi's mutually independent?
Sorry?
The probability that xi is Pareto optimal, are these random?
These are in fact mutually independent. And the argument is, suppose I tell you that point x1 is Pareto optimal. What have you learned about the ordering of the points to the right of x1? Nothing.
That they need to be lower in height than this point?
Well, but I've told you that they're lower in height. So all that means is that the points further, that means that the points further to the left happen to be below, which means I've got n minus 1 points in this smaller rectangle uniformly distributed. I haven't learned anything. Remember, the only thing that matters is the order among those n minus 1 points, the relative order of their heights. Saying they're all below this line doesn't give you any information doesn't bias 0.3 being higher or lower than 0.5. They're both below that line. That's all I've told you. You can actually say this in terms of permutations as well. So if you imagine, okay, there's some number of permutations where problem 0.3 is optimal. Okay. Now I tell you that 0.1 is optimal. The number of permutations where 0.1 is Pareto optimal is n minus 1 factorial, because I know that 0.1 has to be first, and the other n minus 1 I can permute however I like. And then I look at how many of those permutations has 0.3 being Pareto optimal. It's exactly the same fraction out of n minus 1 factorial as originally I had out of n factorial.
Being below, now that you've restricted this point to be below a certain height,
Yes?
hasn't this changed the distribution? Because earlier it was equally distributed from 0 to whatever.
But remember what we're comparing here. I've changed the distribution of y-coordinates. That's true. Instead of being uniform across the entire square, it's only uniform up to that slightly lower ceiling. But the condition whether a point over here, point I that I've labeled there, being Pareto optimal, only depends on how the y-coordinate of point I compares to the y-coordinates of points further to the right. All of those points have been squished down the same way. So the relative orders haven't been, the probability of a given permutation of those points vertically is still uniform. Because everything's been squished, but nothing's been reordered.
Can you also make the same argument when you know that among the endpoints, leaving out the ith point for all other points, you know whether they're Pareto optimal or not. Then you bound the ith point with a lower floor and a higher ceiling.
Yeah, basically. I mean, the way I would make this argument is actually by induction. I would say, if I know that the first point is Pareto optimal or not, I've gained no information about everything else. By induction, everything else is mutually independent. Okay. So, yes.
Yeah. Does I don't know apply to subproblems?
Yes.
Oh, okay, cool. Thanks. I don't know.
Well, so the problem is, if you're trying to get K heads in a row, the problem is that if you get the tail immediately, you start over.
like all the randomized algorithms.
You don't wait until K. So really the way to, one way to imagine this is, what's the probability of getting K heads starting from scratch? What's the probability of getting K minus 1 more heads getting already set 1? Probably like K minus 2 heads getting and each time you fail that, the answer turned out, it turns out to be, I think it turns out to be 2 for K.
Well, that's what made sense.
I mean, try for K equals 2 first.
Right.
Then K equals 3 usually.
Is that in order? It's ordered through key.
Ordered by search case.
All I saw
So the mutual independence is the highest
take everything that they're good
form of independence.
Yes.
So if I have it correctly, it means that given information about any subset of the other random variables, the distribution over a random variable doesn't change having that information. You give me any information about the other nodes, I will not change the distribution.
But I mean, another way of expressing that is the probability that 1 and x2 equals 0 and x3 equals 0 and x4 1 and so on is equal to the probability that x1 equals 1 times probability times probability. And so this is the form that I would actually say. So I would say, if I know this, does it change the probability at all?
Take anything that's like,
No.
take anything that's,
I mean, the conditional probabilities
pleasant,
are the same,
take the right
whether this is a 1 or a 0.
the
or
rightmost one is right off. Look at the next one.
And then, I mean, there's effective proof of this.
Sort twice and then do either linear or.
Right, so,
For
these nodes for the I of K variables.
Work with it, yeah.
So,
That I of K is usually independent.
yes, for all I less than K and I of K
I mean, you can do that too,
for
but
all
it's sort and divide plus divided
greater than K.
which is
These are mutually
asymptotically the same thing as sort and sort.
and these are mutually independent.
If you think about it, eventually, like if you're doing sort and you divide it into half, then you.
But collectively, they're not
In
mutually
some sense, you're sorting and you're manually doing merge sort. I mean, there's a way to view it as sort of the same thing. It's not completely,
So for the
but like,
conflict model,
there's a reason
Yes.
why
I was wondering
asymptotically
if you
there's.
prefer that I come early or stay late.
How do you want to do it?
I'd rather stay late because
That's
for the
fine.
most part,
We're going to do it that way.
awesome. So I'll come on time.
Yep.
Great, thanks.
I have a quick question.